take out your highlighters, and we learn a new important counting technique, which involves a combination. Everything we've done so far, we've been putting things in order, where the order matters. And now, we're going to imagine the order doesn't matter. For example, say you're in English class, and you have a choice. You have to read 3 books from English for your English class, but they give you a choice of 4 books. How many ways can you choose your books for your English class? So you pick book 1, book 2, and book 3, and then you say, no, I want to change. I would rather read book 2, book 1, and book 3. And your teacher looks at you and says, that's the same thing. Those are the same 3 books. Right now the order doesn't matter anymore. And so if you picked 1, 2, and 3 as a combination, in permutations, there's 6 different ways we would have called that in permutations, but in combinations, there's only 1. Or you could have picked book 1, 2, and 4. And in permutations, there would have been 6, but in combinations, only 1. You could pick, any other choices? 2, 3, and 4? Is that what's next? Oh, 1, 3, and 4. And 6 of those, and then 2, 3, and 4, and 6 of those. There would be 24 permutations, right? Because if we were counting this with permutations, you'd have 3 decisions. Which book is first? 4 choices. Which book is second? 3 choices. Which book is third? 2 choices. Okay? And every single combination choice, which has 3 things, in permutations, can you see that these are all 3 factorial? Because if you had 3 things and you wanted to put them in order, you could do that in 3 times 2 times 1, 6 ways. So what a combination is it says, take your permutation, divide out the order, because just, where did we divide in permutations? Identical objects, right? We divided when we had identical objects. In a combination, these are like identical objects that we have to get rid of. So we divide by 6 and get that there are only 4 combinations. So we have to now make a decision in a question. The questions are going to look very similar to permutation questions, but you have to read them carefully and decide, does the order matter? So for example, you win a grand prize at some school event, and there's a prize table with 10 prizes, and because you won the grand prize, you get to pick first, and you get to take 2 prizes home. Does the order matter? You say like, oh, I'll take the brand new car and flat screen TV, and then you're like, no, I think I'll change my mind. I'll take the flat screen TV and the brand new car. It's the same thing, because you got to take them home. So we have to ask, does the order matter or not? If the order doesn't matter, it's a combination. And the combination formula just says, take your permutation formula and R factorial, however many items you have, that's how many ways they could be arranged. You have to divide those identical objects out. So the formula becomes here, and this is at the top of page 723, and we will use this a lot. We don't use this notation very much, but this notation is used a fair bit in university courses. Another way of writing NCR is with the N and the R in brackets like that. You know how we hardly use the permutation formula because spaces were better? This formula we will use a lot. Almost every time you see combinations, you're like, ooh, I want to use the formula. And using the formula is actually really, really easy. We'll see it in our first example. Has anyone heard of the Keno lottery before? No. Have you heard of Lotto 649 in Canada? Some of you, yes. Okay, we'll do Lotto 649 after this, but we'll do this one first. to show you how easy the formula is. In a lot of lotteries, and this one even says how many combinations, so they kind of tell you that the order doesn't matter. But in a lot of lotteries, you pick numbers, and it's not like you get it wrong if you got the numbers in the wrong order. As long as you have the right numbers, you're going to win. So what's interesting about this is 80 numbers, and you choose 20 of them. Now the reason the formula for combinations is really easy to remember is not because the notation looks beautiful, right? I think that's how it's written on your formula sheet. The notation doesn't necessarily look beautiful, but it's really easy to remember because the 80 goes on the top. The 20 will go on the bottom, and then the other number on the bottom is just that the bottom two always add up to the top. So if I have a 20 factorial here, I'm also going to have a 60 factorial. And because of that pattern, it's really easy to remember the formula. So if we do type this into our calculator, oh, I think I had it typed in before. There it is. We get 3.53 times 10 to the 18. That's like a huge number. And what's really interesting is if you try to do it bit by bit, if you try 80 factorial on its own, it's actually too big for your calculator. It's too many numbers for it to calculate. So the only way to get this answer would be to use the combinations, which you can find by going to math and then over to probability, and it's the third one listed. Or if you have a different calculator, you're going to need to find out where it is. Okay, but Lotto 649, I think you saw that I had the number up there. The reason, I think, will they write it like this? Is it something like that, or is the 49 higher? Okay. Lotto 649 means there are 49 numbers, and you choose 6 of them, giving you 13,983, almost 14 million possibilities. And what you're going to learn today is if you want to win the lottery, you can. That's not easy. For example, if you just pick one number, your chances of winning are 1 in 14 million. To give you a sense of how that is, I'm going to take this deck of cards. Okay. I'm going to amaze you by pulling out this card and saying, is it the 2 diamonds? Would you have been amazed? I know, it's 1 in, but if I pulled out a card and I got it right, you'd be like, whoa! And it's 1 out of 52. It's not really compared to this. Now, imagine I have a deck of 14 million different cards. They're all numbered. I pull one out, I'm like, is it 17,323? And I flip it over, and no, it probably wouldn't. That would be creased.
How about you try to call every card in the deck in a row?
Oh, I haven't done that. I have to. I should. Let's see.
It's a 1 in 50.
So the chances of winning are not very good. For this reason, I don't play the lottery. Okay? But if, like sometimes when nobody wins, the prize gets bigger and bigger. Sometimes so big they even start advertising it. Like this week's prize, $50 million. And at that moment, I think, hey, we should go to the bank. Because if tickets are $2 each, go to the bank and say, I would like to borrow $28 million. And the banker will be like, okay, why? I want to win the lottery. Chances are the bank won't give you $28 million, but let's say they do. This could be very good. All you have to do is buy all 14 million different numbers, and you would guarantee that you would win the $50 million? What could possibly go wrong?
The fact that it would take way too long to
Yeah, it would take,
buy that many.
that's a long time to write them all out, and then you have to find the winning one after you win. True, but for $15 million, I could spend a week at that, I think. What could possibly go wrong? Somebody else wins. And then you have to split it, which is still 25 million. But when you go back to the bank who says, where's our 28 million, you're like,
Rover, return to the gym, please.
short
Get
$3 million.
back to the gym.
I hope that's
Bye.
not a problem.
Yeah.
But you could theoretically win it. And what, yeah, sorry?
There's also just like a philosophy in gambling in general to where once something becomes a certain price, the opportunity cost of it becomes worth it.
Possibly. And that what happens is as it goes higher and higher, what happens? More and more people buy tickets. Eventually, so many people buy tickets, right? The idea of 1 in 52, as far as a probability, means that if you tried 52 times, you could win once. Probability is not guaranteed. Statistics say, though, if you tried this 52 times, I could keep going, keep guessing cards, and eventually you'd be like, whoa! But you also might be really bored, like, no, because it could be a lot of times in a row. But it happens that with this many people picking, eventually someone could, just by law of great amount of guesses, someone could win it, and that's what happens. But knowing the mathematics, I don't play the lottery because I know that mathematically I will just lose. However, they say that if you're playing the lottery and you're expecting to win and need to win, you need help, right? But if that ticket gives you the greatest daydream that you are so excited, like, whoa, what could I do? If, like, holding that ticket allows you to daydream and imagine what it would be like to win. And then you don't win. But if you really enjoyed that daydream, it might be worth the $2 for you.
The problem with that is I have heard of what happens when you win the lottery, and it is never good.
Maybe not, but it's still, someone wanted to give me 50 million, I'd be like, oh, okay, I guess so, right?
Winning the lottery can legitimately just ruin your
Could
life.
ruin your life.
Not
Often. But, yeah, okay. So I heard a story. All right, questions for practice on this one. 4, 5, and